Okay, hi everyone. I'll be presenting on lecture 7, I think, which kind of covers a bit about RNNs and some mentioned topics, but not really elaborated on our PCA and entity embeddings. So I'll be talking a bit about that, and feel free to correct me if I say something wrong. The first thing that Jeremy started with was the movie lens dataset, which they were kind of creating predictions for. And what really, so last time we talked about bias in the movie ratings, and this time he wanted to create a sort of embedding space for the movies, and he wanted to show us how we can visualize it, because 50 dimensional space embedding is not easy to visualize or understand the patterns in data. So he pointed that, he mentioned PCA as a way to reduce dimensions, and here he used PCA to reduce from 50 dimensions to 3 dimensions. And what PCA exactly does is it identifies that some dimensions are more important than others, in the sense that it identifies that it identifies patterns in data which kind of show that some dimensions are more important than others. So in this case, this is a toy example of biology in which cell 1 counts and cell 2 counts, you can see, are kind of correlated. So taking these two as separate features is probably more intensive in terms of computation and adding more stuff than just taking an axis which goes along the slope. So what PCA does is it identifies new axes along which the data can be transposed, and you can just take that axis, and that's the new feature that you can use. So here you can see that principal component 1, principal components are numbered in the sense that how much variance they have along the axis. So principal component 1 will always have the most variance, and principal component 2 will have the second most variance, and so on. So here you can see principal component 1 has the most variance, and principal component 2 doesn't have as much. So you can, if you want to reduce this to 1 dimension, you can just take the principal component 1 as your feature. And what it does is it essentially maps the endpoints as the two extremes of the axis, and in the intermediate points it gives them new values. So you can see that the rightmost point is A and it's been given 10, and the leftmost point is F and it's been given minus 14. And these can be mapped onto the input space, and you can generate your new feature vector, which can be used to classify clusters. Another method of dimensionality reduction is TSNE. SNE stands for stochastic neighboring embeddings. So here we saw in PCA that it's useful for data that is kind of linearly separated. But if you want to visualize data which is kind of non-linearly separated, or you can see like data in concentric circles and stuff, you can use TSNE for visualizing. It's more robust in the case that it can visualize data more easily. And one more difference is that PCA does not have any parameters, whereas TSNE you can kind of give it a parameter which kind of stresses what the cluster size should be. So if you kind of have a good idea of the data, you can give it a parameter for cluster size, and it'll improve the visualization. So yeah, that was about PCA and TSNE. He uses that to reduce dimensions so we can visualize the data, and he'll come back to it after he talks about entity embeddings. So in this paper, what they're doing is they are creating new embeddings instead of one-hot embeddings, because it improves performance on most of the machine learning classifiers. Like here, you can see the results that he showed up. MAPE is mean absolute percentage error, I think, and he shows that the new embeddings which are generated with EE means entity embeddings, perform considerably better than the ones without. So you can see that neural networks has improved, random forest has improved by quite a bit, so has GBM. So what happens in this is that you input the one hot layer, and what it does is that it generates a weight matrix, which kind of maps the one hot encoded layer to new embeddings. So because this is one hot, the weights are itself the embeddings, and these are the weights which are sent to the dense layers, the fully connected ones. And since this is this is sort of like a neural network. The weights are what are learned over this neural network. So that's how it generates the embeddings, and these embeddings are then sent to you know like if he was doing this paper was done on Rossmann, the Carroll competition. So when these new embeddings were sent as inputs, these were the differences in the errors that were observed.
But here I noticed that the improvement over the neural network is marginal, right, compared to the other improvements. The KNN improvement is very obvious, but the improvement over the neural network is little. Is 0. Yeah, correct. It's 10%, right? The one is 10.1%, is 9.3%.
I mean, it makes a lot of sense because the neural network can do
That's my point. Yeah. So the first layer of the neural network is kind of the job for the EE.
Yeah.
This is not the same neural network that he tests on the data.
Yeah, but I mean, still, the architecture of the neural network closes, so it can kind of do that a little bit on its own. So
that's right.
The improvement there is not good. I mean, I created Boosted Tree is doing something completely different. So this embedding helps it a lot.
Yeah. Okay, and so this is a screenshot from the lecture itself. So the entity embeddings kind of when he mapped these onto, so when he used PCA using the entity embeddings, he found that the stores, so the Rossmann data has information on store location as well. So when he mapped PCA onto those features, he found clusters among cities, which were shown by the features that he mapped onto the PCA, which is very similar to where their geographical location was.
Can I add something in German to that?
Yeah.
It might look weird to you that Berlin is actually in the West, but since Germany was divided until 20 years ago, and Berlin actually belonged to the western part. Berlin is probably a lot closer to the western states than to the eastern states. That actually makes a lot of sense that it ends up on the west.
Yeah.
So it's actually more amazing.
Yeah,
like if you look at it, it looks a little bit, oh, it didn't get Berlin right, but actually it kind of did get Berlin right.
Yeah, that's even more interesting.
This was built off of what data?
The Rossmann store data.
Okay. So the Rossmann store data indicates Berlin stores behave more like other Western counterpart stores than Eastern German stores.
It kind of shows the former Western Eastern divide of Germany. Which happened, which shows up in many statistics still.
Yeah, that's pretty cool. Yeah. So one more point that he brings up is about how to generate embeddings. So he says someone asks him a question, and he says that either to generate embeddings, either you have label data, which you can probably use dimensionality reduction and get the features that are most important. or you generate fake tasks. And one example of a fake task that you could incorporate, and that was incorporated in a Kaggle competition, which being the state of the art, was using autoencoders. So you can get new embeddings by just taking in outputs from the intermediate layers. So yeah, then he comes to RNNs, and a basic introduction of what RNNs do. So CNNs usually find patterns across space, across images, but RNNs are usually finding patterns across time. It's not a very robust definition, but it kind of gives you an intuition. And those are just two helpful links which I thought worth including. So what here the RNN is doing is it takes in the input xt at time t, and then this loop is basically unrolled onto the right, where it takes in the time xt, it brings out an output ht, and the weights are transferred through time. So these are the slides which I took from CS231N, which shows the different ways that RNNs can model sequence data. An example for one-to-many is image captioning, where the input is a single image, and the many outputs which are represented, which are given out, are the caption, the words in the caption.
You can point using the mouse pointer.
Oh, okay. Sorry. Yeah. Yeah, so these are the words which represent the caption. Many to one is an example is sentiment classification, where you give in a sequence of words, and it basically classifies what sentiment is being conveyed. Many to many is machine translation, where if you want to translate from one language or one way of presenting things to another, it takes in a sequence of words and gives out another sequence of words.
Let me ask you guys all whether you understand this. So why isn't machine translation the many-to-many on the right? Why is it the many-to-many on the left?
Many-to-many on the left is a different language, right? English translate to French or German.
German, okay. That's not quite right, but that's a good start. That's the reason why it's offset, and then move to that.
I want to have the last word of the sentence to be able to translate the first one.
Okay. Yeah, it has to deal with a little bit of that. This green box in the middle of the left side, right? The one that's in the center of the 5 is basically a encoding of the entire sentence. Okay, so you have to think in many languages that the word order might be different, or even in the same language. It helps to have an understanding of what the whole meaning of the sentence is before you try to generate an output, right? So that's why it's not the many-to-many on the right-hand side. Many-to-many on the right-hand side would be like, oh, I want to do like something like, I don't know, word-by-word translation. Or if you think of each unit, each of these boxes as a sentence, maybe that would be like automatic speech translation, right? Where each sentence is one box, right? So each sentence could be represented by the many-to-many on the left, right? Where you take an entire input speech sentence and then you think about it and then you translate it into Chinese, you translate it into Malay, you translate it into Tamil or whatever. Okay, so that's the difference between this. And just to make clear about this, what do we call it when we do this work from the green to the blue? There's an official terminology that we use for this. We're talking about sequence to sequence learning. You'll hear it described a lot.
Is it called output?
It's called output, but there's another official name for it that's specific to like what you would do in a sequence modeling system. It's called decoding. Okay, you may have heard of that before. So what about the red to green? That's the encoding. Okay, so the encoding part, you hear this a lot in sequence to sequence, encoder decoder framework. That means you do this part at the bottom where you get the inputs you encode it into some latent variable like a vector, right? And so at the end of the sentence, like this green box in the middle, you have what you could call a thought vector or something like that, basically, and a vector that represents an entire utterance. Okay, so you hear the word thought vector in NLP, that's what it corresponds to. Okay, so it's just basically an amalgam of many word vectors that are sequentially dependent on each other, so it encodes a whole sentence, right? And then you do the decoding after that. So you take that one representation of a sentence and you're like, okay, if I imagine that this is a thought in somebody's head, okay, the vector represents that, then I'm going to decode it out into a linear sequence of tokens, and that token sequence can be in any language. Okay, so when you hear the words encode, that's red to green, okay, and decode is green to blue. Does that make sense?
I have slightly maybe a sidetrack here. So this usually is being used to model natural languages, right? Like English.
Many times, yeah.
Now, for example, I'm because on my project I'm modeling the tennis. Right? If you look at the tennis action, this player hit this corner and that player hit you that corner, so you can view it as a sequence of actions, just like a sequence of words.
Sure.
But then I realized that there are two problems. One is that language corpus is huge, right. So probably the model can learn the pattern pretty well. But in my domain, I think comparatively, my corpus is much smaller.
It could be.
So how do we deal with that kind of challenge?
Actually, I'd say, and you guys are welcome to weigh in on this, language is very sparse. This is one of the big problems that they introduced embeddings for, is because you can say one word, like I can say football, but I could also use the American term soccer. Right? And there are lots of equivalent words that you could use. That's why languages are so rich, but they make the data quite sparse. So embeddings were, as we talked about last week, a way to consolidate all of that information into a fixed number of dimensions. Granted, those dimensions are fairly high, maybe 300, but it's nothing compared to the 30,000 or 50,000 or 500,000 vocabulary word that's out there on the internet that's actually being used. For your particular case of a video sequence, there are plenty of other sequential models that have been tried many years ago that you could also use. So hidden Markov models, I think many of you have been exposed to generative models. A hidden Markov model or a conditional random field, which is a discriminative model. Those are a pair of models that work very well on much smaller amounts of data, where you have a controlled amount of work. So the RNN is basically a deeper version, if you will, of those earlier types of generative models. It's not to say those are less powerful; they just work under a different paradigm. The discriminative and generative paradigms of sequential modeling. So I have another question for all of you. We heard just now from John Khan that RNNs are good for natural language processing, but you also hear natural languages, well, some tests are well defined using CNNs, right? So when do you use which one? Go ahead. I mean, you don't have to know the answer. In some cases, I don't think anyone really knows the answer which architecture is better. But I'd like you to mull against that, right? You're learning all these architectures. So when do you apply which one? Because like I told you before, it's better to have some hypothesis rather than say, I don't know, I just tried them both, right?
When you are just going for a query, when there is no time relation between sentences, we end up with a one sentence. And CNN can perform a number multiple of sentences.
So maybe we need a sequential model for things that have time series information. That sounds natural. But even some natural language processing tasks, which is inherently linear, right? It's sequential. We still use CNNs for it. Why? Do you know which ones I'm talking about? Can you remember any tasks or that you've heard of that use a CNN to accomplish a natural language task?
The CNN has the capacity to capture the long relationship between classified and classified. RNN long distance dependency can only capture but within the long layers capture the labeling words, but for the highlighters we can capture long. In this case, the scene is better to capture long.
Okay, that's a really good thought. That RNNs are supposed to capture sequential information, but if you've heard more about RNNs, basic RNN structure, it loses its capacity to model things that are way in advance, right? It's got this Markovian assumption sort of built in that after a while it forgets what it remembered long ago. So I think you have mostly been exposed to at least the terminology of LSTM and GRUs. Right? Those are both gated versions of the RNN that helps to retain long-term memory, but still sequential. So I think the key point is, I think what Li Chen was trying to get at, which is that when you need information that's from a longer distance, but the order doesn't matter, okay, a CNN is fine. Okay, so for example, in a task that does well with CNNs compared to RNN on natural language, it's the sentiment analysis task. Okay, for example, I have a sentence. I want to determine whether somebody's happy or upset with it. Okay, if I encounter the word angry, probably wherever it is in the sentence, that's probably a negative sentence, right? Okay, you can manufacture exceptions like not angry or something like that. But for the most part, a sentiment-bearing word in any part of a sentence has the same effect. Okay, so that is a case where CNN does just fine because it is just saying, there's some information somewhere in this picture, in this sentence. I don't care where it is, right? I don't care whether the person's face is at the top, in the right-hand corner, at the bottom. Okay, I just need to identify a face, right? And the same is true of natural language. I want to spot the word angry. Doesn't matter where it is, as long as it's in the sentence, that gives me an indication that this sentence should be classified as negative, right? A presence of a picture of a car in any sentence, in any part of the picture would say outdoor vehicle or something, right? So it's more likely an outdoor image.
Given the same problem, when in this, as you said in the example, RNN will perform better than CNN because it does forget the data sometimes.
Yeah, so there are some tasks if you want to encode things that are very sequentially dependent, that you would want to use an RNN. But even then, I think current thinking is the basic RNN structure is easy to understand and easy to teach, but it's not very good practically because the Markovian assumption that it makes is very strong. Okay, so it will forget things very soon. So even if you don't have a lot of sequential dependency, okay, you don't need to keep things far away. The addition of using a gate such as an LSTM or GRU is sufficiently not so complex that adding it will probably not hurt your performance. Okay, so it's basically I don't think there are many people who use vanilla RNNs anymore. They almost always use some type of gated function to capture slightly more long-term dependencies than short. Okay, if it's even like 3, 4, 5 units away, the RNN tends not to be able to retain that information well. It depends a little bit on other factors like how big your embedding space, etc., how complex the architecture you're trying to manufacture. Okay. So all of those are good reasons to use a gated version like an LSTM or a GRU in response to a vanilla RNN. So if you're doing anything with sequential learning, try an RNN, but it should be your baseline. Okay, it's usually not a competitive thing compared to a gated version.
Okay. Yeah, so another example of the rightmost many-to-many is, okay, I didn't include it, but when you want to classify, videos frame by frame, or you want to annotate frame by frame. So you can have a many-to-many that does not depend on the previous one like the left many to many does. Yeah, so one example of how an RNN works is an example of a character level language model where you're given your input as a character and you want to predict the next character which follows it. So here if you take a small vocabulary like HELO and you want to train it to say hello, you would at first uh, encode the data uh, and we first encode the data and here it's done in one hot encoding. You would initialize the weights that the input would take and weights for the hidden state. Um, then you would go through the training process and you would output like here it's not softmax but you will output a score for the next letter which you would predict. So here in the first step it's supposed to predict E, but right now it's predicting something like O, I think. So this is what happens in the training set. Training data, you're gonna predict something, it's not gonna be right. The loss is gonna you're gonna get gradients and you're gonna improve your predictions. So this is what is going on here, and as you can see, the same weights are being carried forward and improved on as the predictions are being made. So one point in RNNs is that the same weights are carried forward across time. Um, I was just curious if there are any examples where, you know, it's at different points in time, the weights are supposed to be different or something.
You guys think about that? What do you think about that idea that you use different weights, W, at different time steps? Or maybe you guys can speak to why we use the same weights.
Okay. I can come up with one. No. I wanted to say I can come up with one example where you should use different weights, but because like in sentences and actually many German words, the first letter tends to be capitalized.
Right, for nouns,
so
right?
Yeah, for nouns. So it kind of has like the first position in a word has is a little different from the others. But again, in the way at least it was presented in the lecture, you just cut it randomly so that gets last. So you don't start at the beginning of a word.
I think you can take a space or a dot to stop, change the weights.
Mm-hmm. Why would you want to do that?
Because this word is independent of the.
Okay, so start of a new sentence means that any word could come next.
Yeah.
So you would want to start with a different set of weights there. Is that right? Okay. Why do we use the same weights in an RNN? I mean, through all of the different words. What's the use in that? That seems sort of absurd at the beginning. But there's a really good reason for it. A really, really good reason for it. And you should know what that is.
Oh, same language, right? English. It's English, so technically consistent.
That's a good try.
One is to reduce parameters.
Is to reduce parameters. Okay. A lot of the reasons why we see the fully connected layers and FCNs at the top of those networks, they're very, very expensive parameterized. Right? You have like 4,000 cross 4,000. That's like a million something odd parameters. That's really hard to estimate. Right? So when you learn these architectures of RNN and CNN, you should see them as subsets of the fully connected network. They're doing that type of architecture for explicit purpose. Okay, they're basically, if you know Bayesian machine learning, priors. Okay, they're saying that you could do anything in the neural network. You can connect anything anywhere. But if you do that, you're going to have a really hard time learning from data. So I want some regularities. If I have some regularities in the data and I impose that on my network architecture, I just simply disallow certain connections, then I can save, right? So the CNN does that, right? The CNN says, you know, you could connect this neuron to every other neuron in the entire visual raster space. But I'm not going to do that. I'm only going to take this free by free patch that I think is going to matter for the classification of this dot, this pixel. And the RNN is doing the same thing. It's saying that, you know, I really don't care which word I'm on. The modeling mostly comes from inputs from the last word, which is the input that it gets. And, you know, some idea of language itself, like what John Kahn was saying. Okay, so I'm going to just use those two pieces of information to determine what's going to happen next. Okay, I'm not going to allow every word at every time step to have a different set of parameters, because the number of parameters in my W is already big enough. I have to multiply that by each word. That's crazy, right? I'm never going to get enough data to estimate those parameters as well. So it has to do with regularization. If you want to use it that way, you can do with priors. Okay, all of those words pretty much the same thing. Mean the same thing, which is using your knowledge to control what the machine can learn without too much loss in value, right? Okay. Now that said, there are good reasons why you might not want to use the same set of W's for every part. Can you tell me what they might be?
I think example in the tennis that because there are two players, player one, player two, so we should have just two set of weights, one for player one, one for player two. So we take an alternative in the sequence.
Okay, that's a really good idea. Maybe player one and player two behave very differently. They have different strategies. In language, you can see this. Different parts of speech have different roles, right? You wouldn't ask a verb to do a noun's job. You wouldn't ask an exclamation mark to do a question mark's job, right? So there are plenty of times when we could think, if we have sufficient data, okay, then we can think about instantiating different W's, okay? A lot of what we see in network architectures has really much to deal with at the current juncture with the amount of data and the quality of data that we have, okay? Maybe, you know, 5 years, 10 years, or maybe 3 months, I don't know how fast science works. From now, we will have architectures that can determine automatically what level of sophistication the model should be given the data quality and the data volume, right? We do this all the times as humans, right? We say, well, we enrich our understanding of a language or a model. After enough repeated experience, I can start to model different things. I mean, this is how you pick up language in the first place. You don't have a fixed W in your head and never improve from there, right? So you develop more capacity to know what language is, to model nouns and pronouns, and to look at agreement and other things like that. That is your natural capacity as an organic neural network, right, to be able to form this. But in the current day and age, we don't have that quite yet, right? We have a fixed number of parameters. We train a fixed model, and we have to first engineer from our understanding how much data there is, what the data quality is, what is the appropriate network architecture. Okay, so what I want to emphasize from that is when you read those archive papers or those deep learning papers, please think about the volume and the quality of data and see whether that fits the model parameters that they are trying to use. If you see a really, really complicated model with, you know, coming from Google, no problem, okay? They have the data. If you see that type of thing coming from NUS, probably we don't have the data to estimate that, okay? It's probably not a good idea, okay? Because we don't have the sufficient capacity, the computational resources, or the access to data that could manufacture a good model. Okay? So there are things to think about when you read those papers. You have to read them at a meta level. Okay, I want to emphasize that. Read strategically, understand why those papers work. If you don't, you will make the mistake of saying, hey, that architecture looks really good. I think I'll try it in my own research, and then blow 3 weeks of work implementing a model that simply will not work with your data because you do not have enough data, or because your data quality is insufficient to do it. Okay, so you need to think strategically when you read. If you don't, you will fall into this trap. Okay.
Okay. Yeah. So In so this is the what happens during test time after you trained your model. Um, you take in the inputs, you have the weights, you output a layer, you convert it to softmax. Softmax basically brings your scores down in a range of, in probability, so that all of them sum to one. It's basically for uniformity. So here it's predicting. Yeah, so here is not predicting the right one anyway. But yeah, so it's predicting O. But anyway, so this is what happens. So here it says that at test time, when you have these softmax losses, you sample the characters, and that's the model that you feedback. So here what could have happened is you have these distributions for each of the letters, the characters, and he sampled the distributions and he got E out of it. So that's what was sent to the next input. One question that I had, which is kind of touched upon in CS231 as well, is why do you sample at test time when you clearly have a probability that shows which one is most probable?
So we need it above a certain cutoff. Sometimes it happens that you want things to be like it should be greater than 0.9. It's not about most. If one thing is 0.5013 and other is 0.49 something, you actually want the probabilities to be quite different to make decision like this.
Okay, so you're saying that if the probability was, 0.95 or something, it would probably have been sampled definitely, and that's kind of the most more accurate prediction. But here it's kind of so, like, I'm not sure exactly. I just wanted to ask why. But what is the advantage of sampling over just taking the maximum?
I mean, if you have a language model, if you just take the maximum, you have a loop of 26, or even you just end up in a small loop, so you repeat the same word. So if you want to generate something longer, you need to sample to end up with, like, for example, let's look at word prediction. If you predict the next word, you always take the most likely, and you have like the man is, and then after is the most likely.
Yeah.
So you have the man is, the man is, the man is. You just
Yeah.
predict three words.
Yeah, that makes sense. Oh, sorry, bad slides. Yeah, so this is basically the recurrent neural network in a nutshell, and basically another diagram. I did want to cover LSTMs, but I'm not sure. I'll just get back to that. I mean, or I could. Do we have time?
I think we have time. LSTMs aren't too hard, so if you want to try to go for it, you can go to Cola's blog too. We used that one for the last vision lecture.
Yeah, yeah. So that's that's a good resource. This. So I picked up these slides from one lecture that I saw, and I thought it was pretty, like, it gave a good intuitive explanation if I just copied the slides and showed it, because it was kind of very clear. So one problem that Prof mentioned with RNNs is that it does not have memory. So if you have a longer sequence, it won't be able to generate correct outputs after some point in time. So one example of what it could be is that I saw Rajan saw Sylvain saw Martin, and Martin saw Radhika. So if you're predicting this sequence using RNNs, like you said, it could get stuck. Like if the model sees that, okay, noun, verb, noun, so it might predict the next noun to be anything. So if I say Radhika saw Rajan, and Rajan saw, okay, what's the next one? Rajan is just as probable as Radhika or Sylvain is. So that's one problem with RNNs. How you can solve this is using LSTMs, which is basically long short-term memory. What that does is it has gates, which allow it to tune the output that you want to see. So if Radhika saw Rajan, and Rajan saw, Sylvain or Martin, it should know that if Rajan saw is the word, then you should forget Rajan in the next output. So that's what essentially a forget gate does. Is basically it chooses which ones of the words you have to forget, and these are some other gates which I'll show as examples of what they do. So in an ignoring gate, it chooses which of the words. Yeah. Okay. Yeah. So this is the new information which comes in. This is the previous prediction. The select gate basically selects which words can be, you know, multiplexed with the outputs that come from here, and the ignore gate basically chooses which of the outputs coming from here you need to ignore. So I'll probably better with an example. So if you have a word that says, okay, you can't see it, but it says Jane saw Spot. Doug saw. Okay, you need a new name here. So the name which is coming from the predictions is one of these three, and you want the output to be saw. Okay, so the previous prediction was a noun, so it gave Doug. You want the next output to be saw because you want the sequence to be Doug saw someone. So here, what this neural network is outputting is a positive score for saw based on what it's learned, and a negative score for Doug. Here in this example, it doesn't do ignoring. I kind of uh, like, because I didn't have an implementation which did that. Probably not comfortable with explaining what it does because probably won't be clear.
Which one?
Ignoring.
Okay.
Does anyone want to butt in? And
what's the difference between ignoring and forget?
Good question. Do you guys know?
I mean, there's some memory thing, so that seems to be different. But
Yeah. Okay. So I'd like you to think of both LSTMs and GRU as having a separate set of state that's being kept at each time step. Okay. So in addition to the input that's coming in, the observed information, like right, it has a latent variable that it keeps track of at every state. It's sort of like a Markov model. Okay, and there are two functions that need to happen. One is, what do you care about from the input, and what do you care about from your memory? Okay, so those are the two parts. Okay, ignoring, I think, means not thinking about putting something that you've observed into memory. Okay, so for example, when you go through a sentence for sentiment classification, you might see the word car. Well, car has nothing to do with whether you're positive or negative. So I'm going to ignore it for the purposes of remembering whether the sentence was positive. Okay? Forgetting means there was something in my memory, and because I chose not to ignore it, I need to know what to forget in memory. So if I see the word very, for example, I need to remember from the previous state that it's being modified. So when I see the word happy at the next state, that has to multiplex together as this add operation with the memory from not ignoring it to storing it in memory, that suddenly the valence of the sentence was extremely good, very happy. Okay? On the other hand, there could be some times when I see the word angry after very happy, and I want to replace what I had as my valence earlier. I want to forget all about very happy. I want to replace it with angry. Okay? And that's what the forgetting gate does. It says, you know, you were thinking this before, but you know, it doesn't matter anymore. The person's now angry. I want to replace my state of mind with that. Okay, so that's what the forgetting gate does. Okay, the selection is also about passing the observation on to the prediction. Okay, so the bottom 3 lines are about the latent variable, about what's passed from state to state. Okay, so in the sentiment analysis task, it could be, you know, how I feel about the sentence as it's progressing. Okay, but I could be doing another task as well. Okay, so at every point in time, I might have to make a prediction. Okay, that could be about something else. Okay, it doesn't have to be about sentiment. Okay, I could say I'm going to have a LSTM for sentiment because I think sentiment informs another task, like whether to buy something or not. Maybe what the binary prediction is the person going to buy something or not, and I think sentiment is a useful piece of information to encode. Right? If that's the case, then I would maybe have an LSTM line to say, okay, what's the sentiment of the sentence? I'm going to have a latent variable that encodes sentiment. But I'm actually supposed to predict whether someone is going to buy it or not. So the prediction task comes at the top, right? You have this part at the lower left that says what's the observation. It goes into the selection part, meaning from that observation, what bearing does it have on the prediction task? Okay, not bearing on the memory task. Okay, you can see those are 2 different things, right? So that's why there's a bottom line there at the bottom that says, what does this have to do with the memory? Okay, the latent state. And the top line selection bar, which is what does this observation have to do with the prediction task? Okay, now the prediction task itself, as you can see there, there's a cross, right? The cross means in order to make the prediction, I need to know how the current input can help the prediction, but I also have to take into account how I currently have a latent state. What does the latent state say about the prediction? Okay, both inform me of that. Okay, so you can think about that. The RNN. What does the RNN look like here? Where is the RNN in this picture? There is an RNN in every LSTM. Every GRU has an RNN. It's just that some of these things are turned off, right? Because you can see that the LSTM is just keeping extra stuff around. It's keeping an extra set of parameters to help you do the forgetting, ignoring, and selection. Okay.
Is my understanding correct that if we want to reduce this LSTM back to the normal RNN,
yes,
then let ignoring to be always no, always don't ignore anything, and let forgetting to be never forget, right? Basically, you learn the previous one.
Forgetting is only based on how old your memory is. So you basically, after a certain amount of step, you forget something. So forgetting is not based on your input; it's just based on how many steps before you saw something. And if that's like too long ago, you forget it. And I think selecting is you just select everything you have in memory.
So do you know which things are in the RNN and which things are specifically LSTM? If you just like take an eraser and rub out components, this is a great final question, actually. Which parts do you rub out to get back your basic RNN?
The ignoring, forgetting.
Okay,
and
this gate is gone. Okay, that's partial credit. Okay, what's next?
Forgetting.
Selection is
that's gone too. Okay, 1, 2.
Selection is always 1.
Selection is always set.
There'll need some forgetting based on time steps.
Right. Actually, the RNN doesn't forget. The problem is it remembers everything. So the thing is that everything gets stuck together and has no differentiation. So because you're usually at the current time step, you're trying to put that into memory. And all the previous time steps are, sort of compounded together into a single representation that's glued with this one. So in some ways, you've got a exponential loss, right? Because every time you're getting 2 inputs and you're saving 1. Okay. So after 2 time steps, you only remember 50%. After 3 time steps, you only remember 1/4%. So it's like, parenting. Like your grandparents, you're 1/4 for grandparents, you're 1/8 for grandparents, etc. Okay, so you're right. These two layers are basically gone. All right, they're not there in the RNN. Right. Basically, you have the observation, you have the hidden state, and these two get multiplied together to get the output. Okay, so this middle part here, that thing, this gate, this gate, this gate, this gate, and this network and this network, these two weights gone. Okay, then you have an RNN. Okay, clear? Okay, please remember.
Yeah, so basically what the forgetting gate learns is it'll basically output Doug because it's already seen Doug very recently. So that's how it works. If it's seen very recently, it'll add a higher weight to that to forget it. So in this case, what it happened was, wait a sec. Yeah, so basically what happened, hey, I'm not sure. Okay, so my understanding is that the forgetting gate should output a positive score for Doug. And when you add it to or something, or a negative or a positive score, it basically cancels out the Doug that it was propagating forward, right?
What was your observation? Your observation was Doug. In your previous utterances, you had Jane saw Spot. Is that right?
Yeah.
Okay. So what is the memory line trying to keep? Is it trying to keep who is currently being discussed?
It's trying to output. So forgetting gate should basically tell the propagate that you need to forget Doug.
Forget Doug. Okay.
Because you need to have saw as the output, right?
It depends on your task. So I'm not sure what your task is.
Doug saw someone.
Doug saw someone. Okay. Okay. Yeah, you need to. I'm not sure whether this is the right task, but I think you mean what did Doug see, or what's the output at the next step, right?
Mm.
So Doug shouldn't see himself, right? So he should have been ignored. If he was in memory for some reason, because maybe a previous utterance talked about Doug, then he should be dropped. What I would see in this type of utterance where you say Jane saw Spot, Doug, blah blah blah, then maybe I would want to forget Jane, meaning that if I was to do a prediction like the next word, the next sentence, does it start with he or she? Okay, then I would say most likely I'm going to talk about he because Doug is male, and that Jane because she was in the previous sentence, but was previously kept in memory before this step. Jane would be in memory because that was the last person I talked about, right? But when I come to see Doug, that means okay, there's a new center of attention. Okay, so I'm going to put Doug in memory and drop Jane from memory by using the forget gate to forget Jane, and replace that memory with Doug. And then when I need to generate a pronoun later, okay, that generation will say, oh, Doug somehow through this whatever embedding matrix will signal that there's a male masculine pronoun to be. Okay, but I'm not sure exactly what the task is here.
I think the example you try to say that try to memorize that the verb is in the past tense. Saw. So somebody saw. So dog must be saw. It's not will visit, or it's just try to memorize. Is it?
It could be. I'm not really sure what the task is. Do your slides tell you what task you're trying to do? Does it get to a prediction? It says, oh, what's the next word? Is it?
Yeah.
Okay, so it's a word prediction task. Okay. Yeah, maybe it's to output Saul next, because as John Khan said, you saw both Doug and Saul previously, but because you have Saul as the past tense from the previous sentence, you want to retain that tense in the current output.
Yeah. Yeah, probably should have revisited the slides first. This is what it is doing. So here in the next example, you want to. So this was the previous collected possibilities that led to a prediction for saw, and then it outputted that you should forget Doug. And when you output the next word that should follow saw, which is either of these three nouns, it sends in Doug, and the forget gate sends out Doug, and you realize that you need to forget Doug, so the next output should be Jane or Spot.
Okay, so this was the earlier version that we talked about, right? You just mentioned Doug saw something, but he can't see himself. It doesn't make sense. It's not supported by the corpus that you've trained on. So then it has to be one or the other. Good.
Okay. The one thing I think the reason that I got confused was that initially, I think the LSTM starts off with having nothing to forget.
Mhm.
So because it was an initial state, I forgot. I thought it was already, running.
Okay.
So I got confused on why it didn't forget anything.
Okay.
Sorry for that.
No. This is not meant to be lecture. It's meant to be discussion. Unfortunately, I have the habit to lecture, so apologies for that.
Yeah, so this is basically like an overview of what an LSTM holds over an RNN. So yeah, this is taken from Christopher Ola's blog, and this is basically so the network here is the same as the network above. So it's not, probably should have taken something that's marked, but this is how you implement it in code. So you have the forget gate. You have the in CS231. It's called the gate, but
Yeah,
here
they also didn't know. Actually, it's not the gate, it's the selection gate.
yeah, and this is the input and this is the output.
Let me ask you, how many hyperparameters does this model have?
This
Can we go back one slide? Actually, I think that image is slightly different from this. That it doesn't have like a ignore.
Okay, let's go back to the other one. Yeah. So what do we have here? With the input gate.
The first one is the forget gate.
This is the forget gate here, right? That's the forget gate. That's
I
somewhere in here.
ignore.
It's the very first.
This
one.
is the forget
This is the
gate.
forget gate. This one here.
Then the second and third one correspond to the 10 each one is the ignore.
I is ignore, right? Or I is
Sorry, so the 10 each one generates candidates to ignore? No, candidates to select.
Select. Yeah.
This is the selection gate, right?
Yeah.
All right, this is the selection gate. This is, okay, what should we attend to? If you think about memory networks, now it's very popular attention, right? So you're saying, what from the input is important to store in memory, right? That's this part here. And then you add it to memory, right? So this part is the forget gate. This says, coming from the previous time step, what do I still need to remember? If I don't need to remember, please discard it, get rid of it, okay? It's independent of what you decide to keep in. From this input you need to put in, right? Then you take the two parts together and you form your new memory. Like if I was very happy before and now I'm somewhat angry, then I'm going to multiplex them together, right? So this is your memory line, right? What you're storing in there, right? And this is why they wrote gate, right? Because this entire mechanism is missing from the RNN, right? You're just going from here, selecting what's important and then using that for an output, right? And then If you select what's important, you can also decide what to keep in your hidden state, which is what RNN does, right? That's the right arrow that's going through the RNN, right? That's this part here.
I thought the gate corresponds to a 10H gate, so it can't be that particular sigma gate. I think the last one is output gate.
This one is the output, right? That has to be the output, right? Because you're going through there.
But then you update your memory twice, or your state. So you update your memory in the actually 3 times. You update it in the forget, then in the selection, and then after the gate, you update your memory a 3rd time.
No, after the output is based on the memory and the
That's an input of the output. Okay, of the memory.
That's coming in this way, not out that way. That's confusing. Yeah.
So the sigma gate is output gate.
And why do I have 2 outputs? Like why I have 2? I have the HT on top, and then at the bottom right I also have some. Where is that connected to? Or what is that connected to?
This is the normal RNN.
Okay.
Right? This is a normal RNN. And this is the memory line that the LSTM is keeping.
So I have an additional kind of RNN memory, like this.
Yeah,
The
this
stack
is
memory.
this is the LSTM version of the RNN memory, right? The RNN memory has no choice. At every time step, it's going to get modified, right? Because it's going to, if you roll this out, right, there's another one of these that says, take as input whatever is coming from the, where is it? Observations, and then putting it here.
Yeah. So XT is the input.
XT is the input. This is the RNN input. This is the LSTM state input. Right. This is the LSTM state output. This is the RNN state output. Right. And this is the prediction or output at the particular timestamp.
I just want to make it clear again. The first one is the forget. The second one is the ignore. The third one is the gate, and the last one is output gate. Right?
Yeah, I think so.
Yeah.
Check Cola's blog for that.
Yeah,
I think these are all from.
According
Cola's
to the
blog.
notation, this is the forget if you go like in sequence.
Okay. Input, forget,
Can't
output,
be
and
because the ignore the input is multiplied by the gate. So the second one must be the
So this is the LSTM input, right? This is the observation, right? There's 2 things coming in here, so I'm a little confused about that.
So like if you look at the equation for the cell state, it takes ignore and does a element-wise multiplication with the gate. So that has to be the middle 2, sigma and 10H.
The I should put just the input, not
What are you saying? Repeat again.
So according to the equation, I mean if you look at the bigger picture, the cell state is updated by taking the forget, the stuff to forget, and the stuff to ignore. Yeah. Right. So the first sigma gate has to correspond to the forget gate.
Yeah.
So
this one is definitely this thing here.
Yeah,
right?
this one. Yeah.
And then
this one is.
we have to calculate 2 parameters. So one of them has to be I, one has to be G.
It makes more sense that the
The
sigma
I has to be this one, right? This is the
Yes,
sigmoid,
yes.
right? The G is the tan H, which is
Yeah.
this one here, right? And then the prediction is formed on the output plus the tan H from the memory cell, right? The LSTM memory cell coming down. Okay.
Yeah.
Cola's blog is pretty clear. I've read it several times, and I always forget what it says. So please go read Cola's blog.
It's 10:24
Yeah,
now.
you gotta go.
Yeah,
Okay.
this is just one modification of LSTM. Just finishing up. So basically here, they combine the input and the forget gates. We'll probably look at it and figure it out later.
Okay, and we can pen this to the next lecture.
Yeah.
Thank you, everyone. See you downstairs. It takes 6 minutes to walk over, so just in time. Thanks, Radhika.
Thank you.